everyone. Welcome into lecture number 10 of linear algebra. In this lecture we're going to talk about linear transformations. So let's start this lecture by writing the definition of a linear transformation. And it is the following. So a mapping, you can think of mapping as just another word for a function, but a mapping L from a vector space V, so from a vector space V to a vector space W is called, by the way, it's possible that this W could be the same vector space V, just another copy of it, but for now we'll just say that this is between two vector spaces. This is said to be, so the mapping is said to be a linear transformation if the following criteria is satisfied. And remember, this is what we're defining, right? A linear transformation. If and only if the following is true. And this is the criteria. So it's L. Remember, L is the notation for the mapping or the function here. L is applied to vectors in V, right? So in this case, we're going to write L of alpha V1 plus beta V2. So in this, and I'll write this down after I get done writing this right here, but I'll write down criteria for what alpha, beta, V1, and V2 are. But in this scenario, this is a linear combination of two vectors in V. So V1 and V2 are in V, alpha and beta are scalars, and therefore this is a linear combination of vectors in V. The transformation, the mapping, is going to be a linear transformation if this obeys the following property, which is that we can kind of distribute over the scalar multiplication and the vector addition. So if this is equal to alpha times L of V1 plus beta times L of V2. All right, and this needs to be true for all scalars, alpha and beta. And we've been doing everything with the real numbers since the beginning of this course. So in this case, alpha and beta are real numbers, and all vectors V1 and V2 in our vector space V. All right, so this property right here, we'll call this property star. This property is called the linearity property of the transformation, and that's what makes it a linear transformation, right? So in general, when you hear the word linear, you think of this property that you can distribute over the operations of the linear space or the vector space, right? We call this a vector space, but another name for a vector space is a linear space. So our transformation, in some sense, respects the operations in the two vector spaces. Now, as I say this, there's something very important to keep in mind here, and that is that on this left-hand side, the scalar multiplication and the vector addition are happening in V. All right, so I'm going to highlight this. But the scalar multiplication and the vector addition, those are all happening in V on the left-hand side of this equation, right? On the right-hand side, look where those operations are. They're outside of the transformation L. So the codomain of the transformation is W, right? And so these operations, the scalar multiplication and this vector addition on this side, on the right-hand side of the equation, those are the operations in W, which remember could be different, right? Because in general, these can be two different vector spaces. So another way to describe a linear transformation is that the transformation or the function or the mapping, whichever word you want to use, let's use mapping because that's what I wrote here. But the mapping L must obey, or must respect is another word for it, must respect the operations of the vector spaces, right? So it must, another way to say it is that it preserves the operations of the vector spaces. So the vector addition and the scalar multiplication are preserved under the linear transformation. Preserved is a little bit of a dangerous word, though, because of what we just talked about, which is that these over on this side, the scalar multiplication and the vector addition on this side, the right-hand side of the equation, are generally different than the scalar multiplication and the vector addition on the left-hand side of the equation. Okay, so let me write down one more thing and then we'll look at some examples. But here's a recommended exercise. So you will see in some texts actually the linearity property is written in two equations as opposed to just one. So the definition that I've given here is kind of the streamlined definition where we just have one equation that defines the linear transformation, one property, right? One defining property. So here's a recommended exercise that you should all do, and that is to show that the criteria, so the criteria in star can be replaced by the following criteria. So in this case, there's going to be two conditions. And these two conditions are going to be, so the same setup, right? We have our L, but their two conditions now are going to be, one, that L of V1 plus V2, so just the sum is preserved. So this is then, we'll call this, I called it number 1 in terms of over here, but this is, we'll refer to this as 2 star later on. So again, vector addition is preserved by the transformation. And then number 2, you can probably guess, is that the scalar multiplication is going to be preserved. So L of alpha V1, we'll say, is going to be equal to alpha times L of V1. So this is the scalar multiplication being preserved, and the vector addition being preserved separately, as opposed to all in one criteria. Okay, and again, this has to be true for all V1 and V2 in our vector space V, and in this case, all scalars are, all real numbers are. Okay, one more definition, just some vocab really. This is just a vocab. But I said up above here that in general, our linear transformations can have a domain of V and a codomain of W. So they can map vectors from one vector space to a completely different vector space. And we'll look at examples of linear transformations that do this in very soon. All right, but it's also possible that a linear transformation could map vectors in a vector space to other vectors in the same vector space. So the domain and the codomain could be the same space. All right, and so this is our definition here. But if L maps V to V, so this is the notation we'll use for our linear transformations. L maps V to V, so a vector space to itself. So if this is a linear transformation from a vector space V to itself, so from a VS, V to itself, so this is the key, then in this case we refer to L as a linear operator on V. So we call this L a linear operator as opposed to a transformation on V. All right, but the key is that you still have to include the word linear. So the word linear is important here, because now it's saying that the transformation L, right, preserves, and in this case, if the vector space is the same in the domain and the codomain, then that means that the operations are the same on both sides of our equations up here, right? All right, so that's just some vocabulary, that this is called a linear operator if the domain and the codomain are the same space. Okay, let's look at some examples now. Some examples of functions that are linear operators and some that are not. So here's going to be our next item, examples. All right, number 1, here's a linear transformation. I'm going to use this arrow notation to define this. So L is going to be a function, at least a mapping, from R2 to R1, all right, or so from R2 to R you could write. And the formula of how it operates on vectors in R2 is going to be L of x is going to equal x1 plus x2. And here, what do I mean? Well, I need to define the notation, right? You can probably guess. But here, x is just the vector, x1, x2, the vertical vector in R2. So the question is this a linear transformation? And we need to check it, right? So we need to check either property 1 star by itself or each of properties 2 and 3 stars, right? 2 stars and 3 stars. In general, it's actually easier to usually, not always, right? But usually it's going to be easier for you to check the 2 properties individually than it is to check this one. Now, it might just be a tiny bit easier, right? It might just be, and honestly, sometimes it won't make a difference. But for the sake of these examples, I'm going to check the 2 properties separately. So let's check the addition first. So we'll check our star. So in this case, we need to have 2 vectors from our domain space. So we're going to say, let's let x equal x1, x2, and y equal y1, y2. So these are 2 vectors in our domain space, right? And then we need to compute the transformation of the sum of them, right? So then L of x plus y, this is what we need to compute, right? This is going to be L of the sum. We have to add them first, right? This is to add them first. So we know how to add vectors, just component by component. And then from there, what can we do? Well, then we can apply the formula. So the formula says, the formula for this function says to add the first component, which is x1 plus y1, to the second component, x2 plus y2, right? And this is now a real number. It's a real number. And at this point, we can rearrange. So then we can just, we don't need these parentheses, right? So the parentheses I wrote because I had to follow the definition of the transformation. I have to write it this way first. But after I've written it this way, then I can rearrange by commutative and associative properties of just real numbers, right? And this can be written as x1 plus x2, then plus y1 plus y2. But each of these, of course, we can use the definition. A definition goes in both directions, right? So we can use this to replace our x1 plus x2 with L of x. And similarly, y1 plus y2 must be L of y. All right, and so now look what we've shown. We've shown, by applying the definition and writing out all the steps, that the function obeys or preserves the operations of vector addition. This is actually vector addition, right? Vector addition for these two, for this operation, right? Now, the next one that we need to check is that it preserves scalar multiplication as well. So this time, we're going to let alpha be a real number, right? Remember, it's got to be a generic real number, and we're going to just use our x, right? We'll stick with our x being x1, x2. All right, and then we plug in. So same deal. L of alpha times x. Step one is to multiply the real number times the vector inside of the transformation. So this becomes L of alpha x1, alpha x2. Right? Alpha x is just, again, we know how scalar multiplication works on the vector space R2. So you do that, and then you apply the formula for L. So L is going to take first component, alpha x1, plus second component, alpha x2. And then what's it going to do from there? Well, now, again, the parentheses don't matter, right? So the parentheses that I've written are a product of the definition of the transformation, the definition, the defining formula, right? Now what can I do? Well, I can now drop the parentheses, they're not required, and then I can factor out an alpha from each of these, because now I'm just working with real numbers, right? So I can write it like this. And then once again, just like we did before, we can notice that x1 plus x2 is just L of x, and now alpha is factored out, right? So this is alpha L of x. And once again, we have started with L of alpha x and done acceptable, legitimate algebraic operations to get this as alpha L of x, alpha outside L of x, right? So these two properties being satisfied are enough once you have verified, once you've done the recommended exercise to show that these two are good enough, right? Then this is enough to show that this L is a linear transformation. So thus L from R2 to R1, which maps by taking our vector x, this is another notation here, to x1 plus x2 component-wise, right? This is a linear transformation. All right, so it's a function which maps a vector space to a vector space, right? That's another way to interpret a linear transformation. It maps one vector space to another vector space and preserves the vector space operations. All right, example 2. I've got 3 examples for this section here, this item. So this one, I want to do again a transformation, or let's just call it a mapping from R2 to R. And this time I want to define L of x to be the magnitude of x. All right, the magnitude of x. So let's first recall how this is going to work. We're working with vectors that start in R2, right? Our domain space is R2. So that means that our x is just like we just did in the last example. It's x1, x2. And its magnitude is, of course, its length, right? So the length of x is the sum of the squares square root, right? So x1 squared plus x2 squared square root of the total. So the question is the magnitude function a linear transformation, right? Because obviously the magnitude of a vector in R2 is going to be a number, which you can think of as a vector in R1. But the question is, does this function, the distance function, length function, magnitude function, however you want to think of this, does this function preserve the vector space operations? So let's check. We can start with 2 star again, right? And so for this one, what are we going to do? We're going to let x equal x1, x2. We're going to let y equal y1, y2. And then let's compute, right? So L of x plus y. Well, this one's got to be added first inside before applying the magnitude, right? So the first thing we do is we add x1 plus y1 in the first component, x2 plus y2 in the second component, and then we apply our magnitude function, right? So this is going to be the magnitude of x plus y, right, which is the square root. I'm kind of mixing notations here, but it's going to be applied to this, right? So this is now going to be x1 plus y1 squared plus x2 plus y2 quantity squared, square root the whole thing, right? All right, now in this one, we could try to do some algebraic operations like we did in the previous one and factor out and, try to get this to be exactly the magnitude of x plus the magnitude of y. But instead, let's look at the other side. What would the other side be? So L of x, we know, is the sum of the squares, right, of x1 and x2 square rooted. L of y is equal to the sum of the squares of y1 squared plus y2 squared square rooted. And if we add those together, L of x plus L of y, we get a sum of two square roots, right? So x1 squared plus y1, x1 squared plus x2 squared, right? Then outside, square rooted plus another square root, y1 squared plus y2 squared. And this has to be true in general for every pair of vectors x and y. And of course, these two, we know from algebra, right? Just from basic algebra, these two are not equal to each other. So the sum of the square roots is not equal to the square roots, right? Yeah. So this is just not equal. Now you can do, I'll leave it as an exercise to, if you don't believe that, just by looking at it, to do some work to try to expand this out and make sure that, you really can't do this, but you can't. So those are not equal. And so therefore, we don't even need to check the next one, right? But this is not going to be a linear transformation. So I'm going to write it here, but then we're still going to check the next one because we will see that actually neither property holds. So this is not a linear transformation. All you need is one negative answer, right, to know that it's not a linear transformation. All right, let's check 3 star though. So for 3 star, this is the one where we want to let x be a vector in R2 and alpha just be a real number. All right, let's try it. So L of alpha x. Well, this one's going to be L of, as we know, alpha x1, alpha x2. So this is going to be the square root of alpha x1 squared plus alpha x2 quantity squared, all added up, square rooted, right? And at this point, we can actually do the algebra that I kind of referred to up here that, you might want to try, but on this one, we just did a comparison. So down on our current one, the scalar multiplication, look what we can do. We can factor this to be the square root of alpha squared times x1 squared plus x2 squared, quantity, all square rooted. And then the alpha squared is now multiplied, right? So that can be factored out. But when it gets factored out, it becomes absolute value of alpha, right? It becomes the square root of alpha squared times x1 squared plus x2 squared, square root. And so this is the absolute value of alpha times L of x. All right, and so this is like almost the right property. We have L of alpha x, but when it comes out, the alpha, because it's a magnitude function, it's got to make it positive, right? So if you had a -2, for example, inside your L, when it comes out, when it factors out, it would become a +2, and that is not acceptable, right? As far as the definition of a linear transformation goes, that breaks the rules. So for both reasons then, for both of the two properties that we need to check, this function is not a linear transformation. So the magnitude is not linear. Okay, let's do one more. So both of these that we've done, we've mapped R2 to R, just R1. Let's do another example, or look at another example, where actually we map R2 to a larger dimensional space. So let's map R2 to R3 by the following formula. So L of, and I'll write this one out as x1, x2, just to remind us that the domain space is R2. The codomain, right, is R3. So the output of this transformation needs to be a vector in R3. And the formula, I'll give us the formula, is x2, x1, and then x1 plus x2. So it switches the order of the first two components and then adds them together to make the third component. So our domain space is a vector in R2. The codomain gives us, the output is a vector in R3. All right, so let's take a look at this one. Same deal. We want to check the two properties, right? So let's let x equal x1, x2, and y equal y1, y2. And then, same deal. This is what you're going to do when you work these out on your own, right? So the transformation of x plus y, step 1, add them together. x1 plus y1 in the first component, x2 plus y2 in the second component, right? Because again, this is the addition in R2. That's why I'm adding them this way. So this is the vector addition in R2. And then you apply the formula. So now when we apply the formula, the first component of the new vector is the second component of this one, right? So it's x2 plus y2. The second component is the first component of the input vector, so that's x1 plus y1. And then the third component is the sum of all of them. So x1 plus y1, parentheses, plus x2 plus y2, parentheses. And that's all the output vector. And now you can probably guess we're going to use kind of the same reasoning that we did on the first one to be able to just rearrange the components of this, right? And then break it up into two separate vectors. So I'll put dots here. I'll leave some of the work for you guys to do, but just by basic algebra, this is going to be x2, x1, and then x1 plus x2, plus outside y2, y1, and then y1 plus y2. And so, of course, if you believe this, so you're going to fill in the details here, but if you believe this, then this is L of x plus L of y. All right, so it turns out that I'm going to leave this last one as a recommended exercise for you as well, but it turns out that this is a recommended exercise. I want you to let x be x1, x2, and alpha be a real number, right? Show that indeed this scalar multiplication is preserved by our transformation. So L of x is indeed equal to alpha, L of alpha x, is equal to alpha L of x for this transformation, and therefore we can call it a linear transformation, right? It is therefore linear. Okay, so please work that out. It's very important. I think you've seen enough examples here in this short lecture so far that you should be able to work this one out yourself. So give that a shot and pause the video if you need to, and then we'll move on to the next section here. All right, in this next item, let's talk about some important transformations of abstract vector spaces. So in the examples that we've done so far, we've only done transformations from R2 to either R1 or R3, but we can define, or we can study linear transformations between any vector spaces, right? We didn't say that they had to be vector spaces like R2 or R3. So let's look at a couple examples that we've seen before and just might not know it here. And then as we move forward in the semester, we will see lots of transformations of abstract vector spaces. And as we know, our favorite abstract vector spaces are the function spaces, right? So here are two very important examples, and I'm going to leave it as recommended exercises for you to check at least parts of these definitions. But one of them is, let's call this one actually L. We can call it L. L is fine. This is going to be a transformation from continuous functions on the interval AB to the real numbers. So transformation from C of AB to R. Remember that CAB is not only a function space, it's infinite dimensional, right? So we can't even write down a basis for this space, but that's okay because we can define how a function would work, how a transformation or a mapping would work on functions in this space. And so here's the definition. It's going to be L of f. Remember, this is defined on C of AB, so the boundary of the interval is defined already. But this L of f is going to be the integral from A to B of f of x dx. All right, so continuous functions are integrable. Remember, integrable is less strong of a statement than continuous, so every continuous function is integrable, and so therefore we can compute this. So I claim that this is linear. Let's check one property together. So I'm going to check property 2 and leave property 3 for you guys. So for property 2, let's let f and g be continuous functions on the same interval from A to B. All right, and then what do we need to compute? We need to compute the linear transformation, or in this case, we don't know if it's linear yet, right? We're checking that, but we need to apply the transformation to f plus g. So we're going to apply L to f plus g, and by definition, what does that tell us? Well, it means that we need to take the integral from a to b of the function f plus g applied to x dx, right? Then start from the inside. So the definition of the sum of the two functions is that it's pointwise, right? So we basically distribute this and write it as f of x plus g of x. That's the definition of vector addition in this vector space, CAB. And from there, now we can use properties of the integral that we know from Calc 1, which is that the integral distributes over sums, right? So this can be written at the definite integral, can be written as the integral from a to b of f of x dx plus the integral from a to b of g of x dx. And of course, now we see exactly how this works, right? Because this is L of f, and this is L of g. Okay, so in all the details, so notice that you have to apply the integral to exactly what's in the parentheses, and then you can use the addition here, right? The vector addition here. You can break it up using properties from calculus, and then notice that everything works out, right? So, as a recommended exercise, you guys verify that L of alpha f is equal to alpha times L of f for this one, but it does work. So the integral, the definite integral, is a linear transformation from the vector space of continuous functions on a fixed interval from a to b to the vector space of real numbers, right? Okay, so the integral is a linear transformation. That's good to know. The next one is, if you're probably already thinking this, but if the integral is linear, then probably the derivative is too. So the derivative works as follows. It's going to be a function from the set of this function, so it's a transformation, I should say. This is why we have different words for this, right? So that we don't get our tongue twisted here. But the derivative, d, is going to be a transformation from the vector space of functions who have one continuous derivative, so whose first derivative is continuous on AB, to the vector space of functions that are just continuous on AB. And remember, we talked about this way back toward the beginning of the semester, but these vectors, C1 is a subspace of C, right? So the derivative, in other words, these spaces both contain functions that have more than just one derivative and are more than just continuous, right? So there's a nesting property here. So review those definitions if you need to. But again, I want you guys to verify this on your own. But 2-star and 3-star, these are pretty straightforward because they're just basic calculus rules, right? But the calculus rules say that d of f plus g, so the derivative of the sum function f plus g, is the derivative of f plus the derivative of g. Write out all the details for this, right? And the derivative of a constant times f is the constant times the derivative. So again, these should be very, very, very straightforward, basic Calc 1 properties of derivative here. But the fact is that the derivative is a linear transformation for us. That's what we care about in this class, right? A linear transformation from C1 to C on a given interval, right? So those are some important examples of linear transformations of abstract vector spaces, in this case function spaces, that we're going to see moving forward quite a bit. All right, so the next thing that we'd like to do is there's one more definition, one more set of definitions that we'd like to talk about in this section. This section is basically just an introduction to linear transformations, and the rest of this unit we are going to spend a lot of time digging deep into properties of linear transformations. But some important definitions that we need are the image and the kernel of a linear transformation. So what we're going to do now is assume that we have a linear transformation. All right, so let's let L from V to W be a linear transformation. So when we say this, when we say let L be a linear transformation, then what we're saying is that this function L, or this operation L, obeys the defining properties, or maybe the defining property if you use this one, right? You remember, it's either this one property or these two properties together. But we are assuming that are given L in this setup obeys those properties, all of them really, right? All right, so now let's make our definition. So the kernel of L, this is kernel spelled with a K like a kernel of popcorn. The kernel of L, denoted by, so we're going to write this as ker of L, K-E-R of L, is the set. So this is a set. So it's the set defined as following. I'll write it in set builder notation. But ker of L is the set of all V in V. V is the domain space, right? All V in V such that L of V is equal to the 0 vector in W. I'm going to even put a W there. So L of V is equal to the 0 vector in W. So what is this? This is the set of all the vectors in the domain that map to the 0 vector in the codomain. All right? So all vectors in the domain that map to the 0 vector in the codomain. All right, that's called the kernel of our transformation, our linear transformation L. All right, the image of L, you can probably guess what this is. This one, the name kind of is more suggestive, right? So the image of L, that's not exactly what I want to say. So there is not an image of L, so I need to be more careful, sorry. So here's what we want to do. Let's say further now, let's let S be a subspace of V. Sorry, so let's let S be a subspace of V. Remember this notation with the less than or equal to sign. This means that it's a subspace. So let's let S be a subspace. It's important here that we've started off with a subspace for reasons that we'll see soon. So when I say it's important, it's not required, but it is important, okay? So you could do this you could define what I'm about to write for any set, but we want to keep in mind that we're defining it for a subspace, okay, for a subspace. So the image of this subspace S, the image of S under L is the set, let's give it a name again, so denoted by just plain L of S, all right? So this is the set, and the notation here should suggest exactly what the set's going to be. It's going to be L of S is going to be all the W's in W such that W is equal to L of V for some V in our subspace S. All right, so what is this? This is the set of all the outputs of the map L when it's applied to all the vectors in S. So you apply L to the entire subspace S. You can think of it as doing it all at once or one vector at a time, whichever works better for you. And then the set of all the outputs, that forms the image. Okay, that forms the image. Okay, so again, notice that we are defining this by a subspace. This definition, though, as a set builder definition, is perfectly legitimate for any set S or any, single vector, discrete set, whatever you want. So you could define this for any set S, but we're going to reserve the name image of S. This name image we're going to reserve for when S is a subspace of V. All right, and the reason for that is the following theorem. All right, and it says the following. So if L maps from V to W, so if this is a linear transformation, so if L is a linear transformation from V to W and S is a subspace of V, I'm going to use this notation again. Remember, if it's a rounded contained symbol here, that just means subset, right? But this less than or equal to symbol means a subspace. Then the following are true. All right. Then the kernel of L is a subspace of V. All right. Again, same notation. Kernel of L is a subspace of V, and L of S is a subspace of W. So the image of S is a subspace of W. So this is the key to our needing S to be a subspace, right, when we defined it. But the point here is that if S is a subspace to start with, the kernel of L is always a subspace of the domain space. And if S is a subspace of the domain, then its image is a subspace of the codomain. So a linear transformation preserves subspaces, actually. Okay, so that's what this is saying. All right, the proof of this is a recommended exercise. So you guys should be able to work this out. So recommended exercise, just work out the details. You start with the subspace, you apply these two definitions, and show that, again, you have a subspace. So remember that the criteria for checking a subspace are that the subset has to inherit the vector addition and the scalar multiplication of the total vector space, the ambient vector space, right? The defining property of a linear transformation is essentially the same, right? That the transformation has to preserve the vector addition and the scalar multiplication within the respective vector spaces. So all you have to do is carefully put together those two definitions, right? The definition of a subspace, the definition of a linear transformation, and carefully make sure that those operations of vector addition and scalar multiplication are preserved. Okay, so I think you guys can do that one on your own. Give it a shot, and let me know if there's any trouble with it. So to end this lecture, let's just do an example where we actually try to find for a specific transformation and a specific vector spaces, obviously, a subspace. Let's try to find the kernel of a transformation and an image of a certain subspace for this following transformation. So let's let L map, this time from R3 to R2. So now we're going from a larger space to a smaller one with the following formula. So again, I'm going to write this in this kind of arrow notation. So notice that this arrow doesn't get when you're telling what the domain and the codomain are, you just draw an arrow. When you're writing what the assignment is of the individual element of the domain, you put a little, like a vertical line here, okay? And then draw the arrow. And so this vector x is going to map to, so this is in R3, right, from the domain. In the codomain, it's going to map to x1 plus x2 in the first component, x2 plus x3 in the second component, all right? And of course, here, I'll write this out, but what does this have to mean, right? Where x's components are x1, x2, x3 in the usual way. All right, so I'd like you guys to take a minute to try this one on your own. Try to just unpack those definitions that we just wrote down. First of all, I'm going to claim that this is a linear transformation, but you can take a minute to check that as well. So let me write that out actually as part of your task here. So verify that L is linear so that it satisfies the properties of a linear transformation. Then I'd like you to find the kernel of L and the image of S, where S is equal to the span of E1 and E2. Whoops, sorry. I wanted this to be E1 and E3. I mean, I guess it doesn't really matter as long as we have a subspace, right? But let's do it as a span of E1 and E3 from R3. So take a minute, verify that this is linear, then compute the kernel and compute the image of this subspace, the span of E1 and E3. All right, let's see how you did. Again, I'm going to let you guys verify the L is linear, so I'll let you guys do that part on your own. But let's find the kernel. So to find the kernel of L, we need to kind of solve an equation here, right? So we need to find all the vectors that map to the zero vector, right? So we need to find all the x such that L of x is equal to 0. All right, to the zero vector, and this is the zero vector in R2, so I'll put a little 2 down here. But this lives in the codomain, right? The codomain is where the output lives. All right, so let's write it out. Well, we know that L of x on the left-hand side is given by this formula, right? So x1 plus x2 in the first component, x2 plus x3 in the second component, and we know that the zero vector in R2 is given component-wise by just 0, 0, right? And so we need to solve this system. Well, this is a vector equation right now, but it can be written as a system of equations where the first component, x1 plus x2, has to equal 0, and the second component, x2 plus x3, has to equal 0. All right, so we get this system of two equations, three unknowns. So obviously we're going to either have no solution, which is impossible actually because this is homogeneous, right? Or infinitely many solutions. So that's where we're going to be, right? We're going to have infinitely many solutions here. So look what we can do. We can just rearrange this to get each of these in terms of x2. So we can write x1 is equal to minus x2, and similarly x3 is equal to minus x2, just by subtracting x2 from each side, right? And then we can let x2 equal, say, alpha. Let's let this be a free variable. So let this be free. All right, if x2 is equal to alpha, then x1 is equal to minus alpha, and x3 is also equal to minus alpha, right? All right, and then look what we get. So then our kernel of L is equal to all the vectors that are of this form, right? So it's going to be equal to the set of x in R3 that are equal to this vector. So the components are going to be minus alpha, x2 is alpha, x3 is minus alpha, right? And this is true for any alpha in R. All right, now at this point, you can see that this alpha can kind of be factored out. Honestly, because alpha can be any real number, you can swap the minus signs through here and you won't change anything. I'm going to leave it the way it is, but there's ways to do this where you end up with alpha, minus alpha, positive alpha in the bottom, right? That's fine. But what we also notice is that this can now be just, it's a single vector, right? Because it's alpha times a single vector, and that single vector is going to be minus 1, 1, minus 1. So we could write this as a span, right? So actually this kernel of L could be written as the span, so in our notation from linear algebra, as the span of negative 1, 1, negative 1. All right, and so this vector, negative 1, 1, negative 1, that's a basis of the kernel of this transformation L. And so we'll write this one here as kernel of L. This is kind of the most succinct and nicest way to describe this set. So there's our kernel of this transformation. All right, what about now the image of our subspace S, right? So this is the image of the space for which S was the span of E1 and E3, right? Because, again, hopefully you checked that L is linear, or if not, if you didn't check it, then we'll just believe it. But again, you should check that L is linear. But because L is linear, it preserves the sum, right? So we can apply L to each of these individually and then take the span of those two, right? That's just how that works. Because so this is going to be the span of L of E1 with L of E3 just by the properties of the linear transformation. All right, so let's see what these look like. So L of E1, this is L applied to 1, 0, 0, right? And so this is going to be as an output, it's x1 is 1, everything else is 0. So it's going to be 1, 0. So there's the output of L of E1. Similarly, we can apply L to E3. I keep wanting to write a 2 there. L of E3, so L of 0, 0, 1, right? This is going to be what? Well, L of 0, 0, 1 is going to be 0 plus 0, so 0, and then 0 plus 1, so 1. So 0, 1. All right, and so our L of S being the span of these the images of the individual vectors, right? Just because of the linearity of this map L, this is the span of 1, 0 with 0, 1, and then you look at this and you say, wait a minute, those are the standard basis vectors of R2, right? So actually the image of this subspace is all of R2, isn't it? It covers all of R2. All right, and so because the image of the subspace is all of R2, guess what we also learn now? So this is the answer we were looking for, right? The image of S, L of S, is equal to all of R2. But now we can also say, as well, that the image of the entire domain, so L of R3, must also be all of R2, right? Because a subspace mapped to all of R2, therefore the whole space must as well, right? There's just an extra dimension. It's only going to add to this. It's not going to, you can never take away from the image, right? So, yeah, this is how this works. Introduction, a brief introduction to linear transformations. I'm going to leave this one here, and I'll talk to you guys in the next lecture.